Hello, everyone, and welcome back. This video is going to mark a beginning of a new chapter that's going to consume a number of the videos moving forward. And in particular, what we want to move towards through the next few videos is understanding infinite series, so adding up infinitely many numbers. And the goal of doing all this is to eventually be able to describe functions in a new way. And that is going to be through what are called the Taylor and the Maclaurin series. Now, before we can get there, we have to start with today's lecture, and that is introducing what a sequence is. And over the next few videos, we'll talk about the properties of sequences, what it means for them to converge, what it means for them to be monotone or bounded, all of these nice properties. And then we're going to see how these sequences can relate to these infinite summations, these series, in the videos that follow that. So everything that follows from here on out is going to be a sequential building until we can get ourselves up to a point where we can talk about functions again. And that's going to be through the Taylor series. So like I said, today we're going to introduce what a sequence is, and we're going to talk about convergence criteria and just how we can describe these things and how we can think about them. So let's jump right in. So in its completely most general form, a sequence is just an enumeration of real numbers. So you might say your first element of your sequence is A1, some real number. Then your second one is A2, and then A3, and A4, and A5, and you kind of get the idea. The point is, this goes forever. So this might, it might have A100, A101, and then it keeps going, and somewhere out here is A9999, A10,000, right? And the point is, for every natural number n, so for every counting number, 1, 2, 3, 4, you can assign an element of this sequence. So this is going to be infinite, this sequence. It goes on forever in one direction. And there are a lot of ways to put these things together. Of course, these numbers can be anything you want them to be. And so sometimes we can describe these things with maybe a general rule. So for example, we might tell you, or you might be told maybe, that the nth number in this sequence is 2 times n. So what does this mean? You're essentially enumerating all of the even numbers. So A1 is 2 times 1, which is 2. And then A2 is 2 times 2, which is 4. A3 is 2 times 2, which is 6, and so on and so forth, right? So this is an enumeration of every single even number. And if I have a particular even number, for example, 100 I'm interested in, well, then that is the 50th element. I can find that because I can set up an equation that says 2n is equal to 100. And now I get n is equal to 50, which tells me that A50 is equal to 100. So this is a perfect roadmap, right? It tells me specifically what every single element of this sequence is based on my index. So in this case, n is what's called an index. Okay, let me give you another example here. So for example, I could take maybe an is equal to the square root of n. So we can do this in terms of functions that we're already familiar with, right? The only difference here is this is sort of like a discrete function. You're only allowed to take values from 1 to 1, 2, 3, 4, and so on. So in this case, I get A1 is the square root of 1, A2 is the square root of 2, A3 is the square root of 3, and so on. So I'm just continually taking square roots. Again, I have a general rule here. And so this tells me, how to find, if I wanted to know what A100 was, what the element at the 100th index, I can do it. It's just the square root of 100. It would be 10. So let me give you another example. Maybe I could give you minus 1 to the power of n plus 1 times 1 over n. Okay, So the formula looks a little more complicated, but it's nothing special. It's still just a function. So when n is equal to 1, I get minus 1 to the power of 2. So minus 1 squared, that's positive 1. And then times 1 over 1, which is 1. Right? So all I'm doing is evaluating function. We haven't done anything new or exciting really yet. I could, in this case, I have minus 1 to the power of 3, which is negative, and then times 1 over 2, so minus 1/2, just evaluating a function. Similarly, a3 becomes positive 1/3, a4 becomes minus 1/4, and so on and so forth. And you can see that every second element is positive, while the other ones are negative in this case. Okay, you can keep playing with this. You can define all kinds of other sequences. You could maybe even look at something like this. And really, nothing is out of bounds here. You can use any sort of known function you want. You're just evaluating them at discrete values. So if you have n minus 1 over n, in this case, you get 0. And then the next term here is 1/2. And then the next term here is 2/3. And then the next term is 3/4, and so on and so forth. Now, it might not always be the case where you're given a general rule. Maybe you can be given something like a sort of prescription. So if you know what happened previously, you can find what happens next. So maybe I could say that the next element in the sequence, or maybe let's just write it as the current element, is 2 times the previous element. And if you're going to give a recursive definition like this, you also have to be given some initial point. So let's say the first one was 1. And then in this case, so a1 is 1. And then a2 is 2 times a1. So this becomes 2. And a3 is 2 times a2, which is 4. And a4 is 2 times a3, which is 8. And a5 is 2 times a4, which is 16. And so on and so forth. And so in this case, you're getting all of the powers of 2. So you can actually write down a general formula here. You can say that an is 2 to the power of n minus 1 in this case. So in this case, we kind of got lucky. We were given a recursive definition, but we were still able to find an explicit description, just like the functions that we were given in examples 1 through 4. Now, the last one that I want to show you is very famous. People talk about it a lot. You've probably heard people talk about it, but that is what's called the Fibonacci sequence. And it says that the current element is the previous one plus the second to previous one. And in this case, because you're using 2 previous ones, you need the first 2 given to you. And so I know that a1 is equal to 1. I know that a2 is equal to 2. And in this case now, a1 and a2 are both equal to 1, I'm sorry. And then a3 is a1 plus a2, so that's 2. And a4 is the previous 2, so 2 plus 1, so that's 3. a5 is 3 plus 2, which gives me 5. And a6 is equal to 5 plus 3, which gives me 8. And the last one I'll do is a7, that's 8 plus 5, which gives me 13. In this case, we don't have an explicit formula for this. So you're going to, if you want to calculate what the 100th Fibonacci number is, you need to calculate everything up to 99, because you need 99 and 98 in order to calculate 100. Okay, so generally, we're just going to be given a sequence of numbers. There's lots of different ways to write this. Sometimes we'll just write it as, sometimes we'll just write it as an. That is how we denote a sequence. That's how we denote elements of a sequence. Sometimes you'll see people write it like this, as a set an, Sometimes you'll see people even tell you what n runs from. They'll say n runs from 1 to infinity. So this is sort of like a little integral, same kind of notation. It says the bottom one is where you start, the top one is where you end. That kind of should remind you of maybe an integral that looks like this, where you have the upper and lower bounds. So there's lots of different ways to write these things, and we'll sort of use them all interchangeably as we get better with them. But what I want to focus on for a moment is maybe my fourth example here. Because my fourth example, let me write this on the next page. My fourth example was n minus 1 divided by n. And if you looked at the sequence of elements, maybe you want to put them into your calculator for larger and larger n's, they look like they're getting closer to 1. In fact, we can distribute this n in the denominator over the numerator, and I get this. And if I was to write maybe this function down, so replace n with x, you are very good with functions by now, I imagine. So you know that as x goes to infinity, this thing converges to 1. Well, then we would expect that the same thing happens with this discrete sequence, right? We have the same sort of notion of convergence when we talk about sequences as well. So we would like to know, is it the case actually that this thing converges to 1? So this is what's going to occupy us over this video and the next one that's going to follow it, and even the next one that will follow that. We're not just interested in any sequences. We're particularly going to be interested in sequences that actually converge. So, of course, if we care about things that converge, we clearly need a definition for what it means to be a convergent sequence. So let's say the sequence AN, so we're going to write it like this. And the definition here is it converges. So I'll put it in red just to highlight it, to the number L. So L stands for limit in this case. It's a real number. If every positive number epsilon, I'll explain in a moment. Positive number epsilon, sorry. If for every positive number. For every positive number epsilon, there corresponds an integer capital N such that the distance of the sequence elements from the limit are smaller than epsilon whenever n is greater than or equal to capital N. Okay, so then let me continue with the definition, then we'll speak about it. So if no such number L exists, we say the sequence AN, we say it diverges. Okay, so this is probably just articulating something that you already knew. We've been doing this with continuous functions for a long time. We've been taking limits. We've been talking about convergence. So this is just putting it in terms of a discrete sequence, right? So the sort of atoms of elements, A1, A2, A3, A4. Okay, so what does this definition say? It's technical, it's mathy. We're not going to have to use it in this form too much because we can carry over a lot of our intuition that we've used for functions so far. But while we're here, let's talk about this for a moment. This says if you give me any positive number, it can be 100, that's a positive number. It could be pi, that's a positive number. Or it could be ridiculously small, 0.000000001. Okay, those are all positive numbers. Well, what it says is that eventually I can find a capital an integer capital N, so that the distance of the sequence elements from my limit is within a distance of that positive value you gave me, as long as I look at the sequence beyond capital N. Okay, so I know it's technical, I know it's hard to see, but let me give you some examples. Before I do that though, let me give you a little notation. So the notation here is if AN converges to L, we write, so we do the same thing that we usually do for limits. We do for functions. See, I'm even confusing it with functions a little bit because it's so similar. I wrote x to infinity instead of n. Or simply AN right arrow L. So it's basically the same thing that we've been writing. And we call L the limit. So again, hopefully none of this is too unfamiliar to you, because you've been doing this for a long time with calculus if you've made it this far in these videos. Limit of the sequence. Okay, so how do we actually see this this definition in motion? Well, let me give you an example. Okay, so example 1. Let's show that limit as n goes to infinity of 1 over n is equal to 0. Okay, so if I take 1 over progressively larger numbers, I am going to eventually get closer and closer to 0. That's what it's telling me. And you know this intuitively, right? 1 over 10 is 0.1. 1 over 100 is 0.01. 1 over 1,000 is 0.001, right? So we know this. We have a good intuition for this. The question is, how do we actually use the definition to show this? Well, okay, imagine you gave me some small number, epsilon. Actually, it doesn't even have to be small. It just has to be a number. You give me a positive number. I'm going to leave it completely arbitrary. I don't know what it, well, I should know what it is, but imagine, any number could have been picked. So I'm going to show this is going to work no matter what your choice of epsilon is. I can always make this work. Okay, so imagine epsilon is given to us. And then from the definition, we must show, so we're going to use the definition that there exists some capital N such that, so ST, that's such that, that's just my short form, 1 over n minus 0, because my limit L is equal to 0 in this case, is smaller than epsilon whenever n is greater than or equal to n. So if I look at the sequence for sufficiently large indices n, this 1 over this is going to get smaller than your value of epsilon you gave me. Okay, let me explain how this works then. The inequality. So you basically want 1 over capital N minus 0 is less than epsilon. This will hold if 1 over capital N is less than epsilon, which I'm going to invert both sides of this thing. That is the same as asking for capital N greater than 1 over epsilon. Okay, 1 over epsilon is a positive number. I can always find an integer bigger than any number you chose, right? You chose pi to the power of pi to the power of pi. I can find an integer bigger than that. I can sit here, if I've got infinite time, I can just count. Is 1 bigger? No. Is 2 bigger? No. Is 100 bigger? No. Is a Googleplex bigger? Yes. I can always find it, right? I can always just keep adding 1 and I can keep finding a number bigger than another number. That's how the real number line works. So that means that I can choose capital N bigger than 1 over epsilon. So choose capital N bigger than 1 over epsilon. Remember, look at the definition here. It says, if for every positive number epsilon, there corresponds an integer n. So your choice of n is going to depend on what epsilon is. So if you gave me epsilon is equal to pi, then if I choose n bigger than 1 over pi, then I'm going to make this work. If you chose epsilon is equal to 0.1, then if I chose n bigger than 1 over 0.1, which is 10, then it'll work. So to find that if n is greater than or equal to capital N, which is bigger than 1 over epsilon, we have 1 over n minus 0, which is just the same as 1 over n, is less than or equal to 1 over capital N, which is less than epsilon. And that's what we wanted to show. Remember, we must show that there exists a capital N such that 1 over n minus 0 is less than epsilon. And look at the left and right extremes of my inequality. 1 over n minus 0, epsilon. So, therefore, 1 over n, pardon me. 1 over n converges to 0 as n goes to infinity. Okay, so I know that that was hard, right? Let me give you one more example just so we can see how this works. Like I said, a lot of the time we're not going to actually work with this definition, but I want to make sure that you at least understand what's going on here. Okay, let's show that the limit of a constant number, so the limit as n goes to infinity of a constant k is just equal to k. All right, so constant function converges to its constant, where k is any constant. You know this, right? You definitely know this, and you know this from just basic calculus. If f of x is equal to a constant, taking x to infinity, the limit is that constant again. How do you do it with these epsilons? Well, you always sort of set them up the same way. Let epsilon be given. You gave it to me. I'm going to show that it's going to work no matter what the value of epsilon is you gave me. Now, I like to tell myself what it is that I need every time I write these down. So we must show that there exists a capital N, an integer, such that the sequence k minus k is less than epsilon for all n greater than or equal to capital N. Now you can see it, right? There's nothing really exciting to happen here. But since k minus k is equal to 0 and epsilon is greater than 0, we've got that this distance here of the sequence from its own limit is equal to 0 always. We're already at the limit, which is less than epsilon. Again, look at the left-hand side. That's what we start with. The right-hand side is what we want to show that it's smaller than. So we've already got what we need out of this equation. The n hasn't even entered. So this happens for all n greater than or equal to 1, every element of the sequence. So we can take n equal to 1 regardless of the value of epsilon. So therefore, the constant sequence k converges to k as n goes to infinity. So it's, I don't know, maybe it's not that exciting to you, but it's important to see how to work with the definition, right? How to use this notion of epsilons here. Okay, let me give you an example of one that doesn't converge. So example, let's show that the sequence And the sequence is going to be 1, minus 1, 1, minus 1, 1, minus 1, and so on and so forth, diverges. Okay, so first of all, we can write an explicit form for this thing. It's minus 1 to the power of n plus 1. That's how you can get any single element of this. It's just alternating between ones and minus ones. Now, if we go back here for a moment, we have a definition that says if this thing is going to converge to some limit, which I don't know what that limit's going to be yet. In fact, the example tells me this is going to diverge. So there's not going to be a limit. But if there was one, I should be able to find, or I should be able to be given any positive number, doesn't matter what it is, and show that I can get close enough to that limit. And close enough is measured by that positive number, epsilon. Okay, so immediately think about what we've got here, right? We're alternating between positive 1, minus 1, positive 1, minus 1. So everything is staying at a distance of 2, right? Every second element is a distance of 2 from the previous one. And so why don't we take epsilon equal to 1/2? So let's say take epsilon equal to 1/2. Now, if this thing was convergent, I would be able to find elements that are within 1/2 of their limit, right? Because that has to work for every epsilon. It certainly has to work for 1/2. Okay, but then if a limit L existed, we would have, let's say 1 minus L is less than 1/2. And that comes from the fact that every second element is equal to 1. So because every second AN is 1, is positive 1. So because there's infinitely many of those, every second one of them, they have to be, if I look beyond some capital N, I have to have this thing within a distance of 1/2 of the limit. Now, this really tells you that L is between 1/2 and 3/2. Okay, so the only way that that's ever going to work is if L is between 1/2 and 3/2. And that just comes from the fact that 1 minus L is less than 1/2, the distance from 1 to L. Okay, sure, that's fine. This, at least, we haven't made any faults yet. The math is working out. But every other AN is minus 1. And so if L exists, we must also have, minus 1 minus L is less than 1/2. Why? Well, the elements of the sequence have to be getting close to the limit, both the even and the odd terms, right? The ones that are positive 1 and the ones that are minus 1. And so this is the same as saying, 1 plus L is less than 1/2, which is the same as saying minus 3/2 is less than L, which is minus 1/2. Okay, so now look at the two regions that I've drilled L into. I said L is between 1/2 and 1 and 1/2, 3/2. But also L is between minus 3/2 and minus 1/2. So if I just sketch this out on the number line, we can really see that there's no possible way for this to ever happen, right? If this is 0 right in the middle, we're essentially saying, L is simultaneously in both of these red strips. It's in here and in here. So maybe we'll just put a little note and maybe in green. So we have shown L must be in both red strips at the same time. But of course, this is impossible, right? There's no way that a number could be in two places at once, especially when there's no overlap. But this is impossible. Right? So we argued using logic and deduction that no such L can exist. So therefore, L does not exist, which implies the sequence is divergent. Okay, so again, think about how we use the definition to arrive at this. We said that, okay, smarty pants, like if you think that this thing is going to converge, then I get to pick epsilon and you have to show me that it gets within epsilon. So I pick epsilon to be 1/2. There, make it work. And you started working through this and you said, okay, if it has to be 1/2, then that tells me the limit has to be between 1/2 and 3/2. But also, oh wait, right? The limit also has to be between -3/2 and -1/2. So we put the limit at 2 spots on the number line at the same time. Those spots have no overlap, so it's sort of, it's saying that I am in Berlin and I am in Paris at exactly the same time. That's not possible, right? I cannot be 2 places at once, and therefore, something went wrong here. And the place where it went wrong, would collapse this whole Jenga tower, was that we assumed that L existed in the first place. L cannot exist. Okay, so the last thing that I would like to wrap up with here is talk about sequences that diverge to infinity, right? So for example, let's think about a function. Maybe if we have this function, we know, so maybe I'll just put a little line here, separation, it's a new thought. We know that f of x approaches infinity as x goes to infinity. So then we sort of ask the question, what about if we replace x with n? So what if an is equal to the square root of n? So does the square root of n approach infinity as n goes to infinity? Of course, right? And this isn't something that we need to really, this isn't like some weird philosophical thing. It's not one of those weird quirks of math where you get a counterintuitive example. The answer is always yes here, right? But the question is, how do you quantify this mathematically? And so if you'd like to, you can quantify this using the following definition. So we'll close on this definition. And so this one says that the sequence an, and we'll put the actual new terminology in red. It diverges to infinity if for every number capital M, there is an integer capital N such that for all n greater than or equal to n, an is bigger than m. Okay, we'll talk about it in a moment. Let me finish writing before that. So if this condition holds, we write that the limit as n goes to infinity of an is equal to infinity, or just an goes to infinity like this. Now, before I conclude, or before I talk about this, let's just talk about let's talk about the same thing if you go to negative infinity. So similarly, if for every number little m, there is an integer capital N, such that for all n greater than or equal to n, we have an is less than m. Then we say the sequence an, it diverges to negative infinity. So it diverges to negative infinity. And write basically the same thing. So and write, sorry for the zoom, that happened accidentally. The limit as n goes to infinity of an is equal to minus infinity, or simply an approaches minus infinity. Okay, so what does the definition actually say here? Not much more than you probably already knew, right? All we're doing is putting a precise definition on something that we probably already understand. So the first part about diverging to infinity, it says that, you know, this sequence, if it's really going to go to infinity, it can be bigger than any number, right? So you pick a number, right? You pick 10 to the 10, for example. Then I can find, if I look far enough into this sequence, everything in that sequence is going to be bigger than 10 to the 10. Of course, right? If this thing's going to infinity, it's got to be bigger than anything that I can prescribe it to be. Similarly, if you're going to go to negative infinity, pick a number, pick anything you want. It could be super, super negative. It could be minus 10 to the 10, for example. Well, if this thing is going to get all the way to minus infinity, it's got to be smaller than minus 10 to the 10. It's got to be further left on the number line in that case in order to go there. Again, these are probably things that you knew, but didn't really put like a lot of thought into, you know, how do you actually explain it, right? It's something that we've worked with in mathematics, these convergence to infinity or just convergence of a function. You have a pretty good idea of what's going on, right? But then, you know, if I really press you, I say, you know, explain it perfectly to me. That's where sort of things start to break down, because you don't have the technical language potentially to describe exactly what's happening. And so that was the purpose of today's lecture, was to introduce the concept of sequences, just the bare bones concept of a list of numbers, and then give you the precise mathematical language to talk about when these things actually converge, or when they, you know, run off to infinity, when they diverge to infinity or to negative infinity. Again, concepts that you probably already knew. And if it makes you feel better, sometimes, as I was doing for this lecture, sometimes I like to think about what the corresponding function would look like. And then I use my intuition from functions to sort of figure out how things are going to work with the sequence. Now, in the next lecture, we're going to come back and we're going to talk about convergent sequences and little tips and shortcuts that we can use so that, you know, we don't have to do these long epsilon proofs every single time we want to talk about limits. In fact, you know, going forward, you know, 99% of the cases, at least for the remainder of this class, are not going to use those epsilons, right? So I'm going to show you how we can circumvent that, make our lives easier, make things a little simpler.